You might think navigating the open ocean without GPS or a compass sounds impossible. And it does if you only think about today's tech. But for thousands of years, people crossed vast seas. They found tiny islands, navigated huge coastlines, and they did it with incredible accuracy. Imagine sailing for weeks, maybe months, across an endless blue and then hitting a tiny speck of land no bigger than a city block. It happened. It happened all the time. How did ancient mariners do it? How did Polynesians cross thousands of miles of ocean to settle islands from Hawaii to Easter Island? Think about the Vikings reaching North America centuries before Columbus, or the Phoenicians sailing beyond the Pillars of Hercules into the Atlantic. These weren't random drifts. They were deliberate journeys. They used methods that seem almost magical now, relying on observation, knowledge passed down generations, and a deep understanding of their environment. We're talking about a time before accurate clocks, before sextants, even before reliable magnetic compasses were widespread. Yet, these navigators built empires, discovered continents, and connected distant cultures. They didn't have screens or satellite signals. They had the sun, the stars, the wind, the waves, and the birds. They looked at things differently. They saw patterns where we now see chaos. Take the star compass used by Polynesian navigators. It wasn't a physical object, but a mental map of where stars rise and set. This allowed them to hold a course with astonishing precision. Or consider the Micronesian stick charts, maps made of sticks and shells that represented ocean swells and islands. It sounds primitive, but these charts captured complex wave interference patterns that modern science only fully understood much later. People like Thor Heyerdahl, with his Kon-Tiki expedition in 1947, showed us that ancient voyages were possible. In his journey, though controversial in its interpretation of how voyages were made, proved that simple rafts could cross the Pacific. More importantly, studies by ethnographers like David Lewis and the revival of traditional voyaging by groups like the Polynesian Voyaging Society with their Hokulea canoe have demonstrated the living knowledge of these navigation arts. Hokulea has sailed tens of thousands of miles, often without modern instruments, guided by ancient techniques. It makes you wonder, what else did they know? What secrets did the ocean whisper to them that we've forgotten? And how much of this ancient wisdom could still teach us something today, even in our high-tech world? We're going to look at 19 of these ancient navigation methods. They were simple, they were ingenious, and they were shockingly accurate. Number 19 was just seeing the next island enough. People sometimes forget how much of ancient sailing wasn't about epic open ocean crossings. A lot of it was what we call island hopping or coastal voyaging, and this sounds simple. Just sail from one island to the next, right? But even this needed skill. It meant knowing where islands were, their general direction, and how far. And it wasn't always a straight shot. Sailors often had to go against currents or winds, or find safe passages through reefs. Consider the Polynesians in some parts of the Pacific. They didn't always make one giant leap across thousands of miles. Sometimes, they moved from island group to island group, slowly expanding their range. They would colonize an island, build up resources, and then send out scouting parties to find the next one. This strategy of island chains or visual chains was super effective. They knew that if they saw a certain kind of cloud formation, it might indicate land over the horizon. Or if they saw certain birds flying in a particular direction at dawn, it meant land was that way. They used existing islands as staging posts and landmarks, and it wasn't just the Pacific. In the Mediterranean, the ancient Greeks and Phoenicians hugged coastlines much of the time. They sailed from headland to headland, using prominent mountains, capes, and even man-made structures like early lighthouses as guides. Homer's Odyssey, while a myth, shows this kind of navigation. Odysseus is often coasting or being blown to islands that are clearly visible or known to be in a certain chain. The Periplus of the Erythraean Sea, a Greek text from the 1st century AD, describes coastal routes for trade in the Indian Ocean, listing ports and landmarks in detail. It's not glamorous, open ocean stuff, but it was the bread and butter of ancient commerce and exploration. These navigators didn't just stumble upon islands, they had knowledge, they knew prevailing winds, they knew currents, they likely had mental maps or even simple charts scratched into wood or sand. Dr. Athol Anderson, an archaeologist, has studied patterns of Polynesian expansion and often points to these step-by-step movements rather than just single long-distance voyages. He shows how the first waves of settlement often exploited the closest islands before pushing further. It was about managing risk. Why sail into the unknown void if you could see the next stepping stone? And that next stepping stone might be a volcano towering miles above the sea, visible from a great distance. Or it might be a low-lying coral atoll that was much harder to spot, requiring other navigation cues. But the basic idea was that if you could see land, you were safer. Shocking questions still remain. How much pre-planning did these island hops actually involve? Did they deliberately leave one island knowing there was another specific island X miles away? Or was it more opportunistic? And how did they confirm an island was truly uninhabited before moving a whole community there? We know they found many, but how many attempts failed? Number 18, what did floating trash tell them? Driftwood and other debris might seem like just junk floating in the ocean, but for ancient navigators, it was like reading a newspaper. The type of wood, where it was coming from, even the sea life clinging to it, all could give crucial hints about land, currents, and even what lay ahead. This was a sophisticated form of environmental observation. Think about it. You're out at sea for weeks. You see a piece of wood. Is it light and bleached or dark and heavy? Does it have barnacles on it that are common in one area, but not another? Is it a type of tree that only grows on a specific island? These were important questions. Polynesian navigators, for instance, learned to recognize particular types of plant debris. If they found certain reeds or leaves, they knew they were nearing an island where those plants grew. It wasn't just land, it was that specific island. In the book We, The Navigators by David Lewis, he talks about how Pacific Islanders were incredible observers. They didn't just note the presence of debris, they analyzed it. A fresh branch with green leaves meant land was very close, possibly just over the horizon. A waterlogged old piece of timber meant land was further away, or that it had traveled a long distance. And it wasn't just plants. Sometimes fishing, floats, or parts of canoes would drift far from shore. If you found a piece of a certain type of fishing gear, you might deduce that you were in the fishing grounds of a particular island community. This could guide you towards that island. Even the presence of volcanic rock, pumice, could signal proximity to volcanic islands, often carried by currents from eruptions. Archaeological studies, like those done on the spread of materials in Oceania, show how currents distribute debris. A study published in the journal Science in 2011, focusing on currents and their role in human dispersal, highlights how predictable pathways for flotsam can exist over long periods. Ancient mariners would have known these pathways. They would have understood that debris wasn't random, but part of a larger system. The Roman writer Pliny the Elder, in his Natural History, mentions how sailors looked for signs like floating weeds as indicators of land. The Sargasso Sea, with its vast mats of floating seaweed, was known to ancient mariners and was both a landmark and a challenge. But different types of seaweed or even freshwater reeds could tell a sailor if they were approaching a river mouth or a specific type of coastline. This method, while perhaps not offering a precise latitude or longitude, gave context and direction. It helped answer the critical question, am I going in the right direction, and is there land up ahead? It helped confirm dead reckoning estimates or provide a new lead when lost. Still, we wonder, how reliable were these debris signs over huge distances? Did they ever lead navigators astray? And how did they distinguish between debris from a new unknown land and debris from an island they already knew about, especially if they were exploring? Number 17, how did they use falling stars to find their way? When we think of stars, we often think of fixed points, but ancient navigators, especially those in the Pacific, didn't just look at where stars were. They looked at where stars moved. They paid close attention to star trails, or more accurately, the specific points on the horizon where stars would rise and set. This was a highly precise method, much more than simply identifying constellations. Imagine the celestial sphere as a giant dome above you. As the Earth rotates, stars appear to move across this dome. They rise at one point on the eastern horizon and set at a corresponding point on the western horizon. For a given latitude, these rising and setting points are fixed. Polynesian navigators memorized hundreds of these points. They created a mental star compass, which we'll get to more deeply later based on these precise positions. Dr. Ben Finney, an anthropologist and expert on Polynesian voyaging, extensively documented this. He showed how a master navigator like Maupi'e Lug from Sarawal could name the specific stars that rose and set at each of the 32 or more points on his mental compass. This wasn't just the sun rises in the east, It was the star Attic, or a specific traditional name for it rises at a point on the horizon that indicates the direction of island the 10th, and sets at a point indicating the direction of island Y. This required incredible memory and constant observation. When sailing, a navigator would pick a star that was rising or setting in the desired direction and keep the canoe pointed towards it. As that star moved higher in the sky, another star would rise or set in the same direction, and the navigator would switch focus to the new guide. This constant shifting of guide stars, maintaining a bearing, allowed for remarkably straight courses over vast distances. A specific example comes from the Hokulea voyages. In 1976, Maupiailug navigated Hokulea from Hawaii to Tahiti without instruments. He used these star paths. The crew observed him constantly checking the star lines, even when clouds obscured them briefly. He could feel the direction from the waves, but the stars gave him the precise bearing. And they arrived at Tahiti, a small target, after a long voyage. The accuracy came from the fixed nature of these rising and setting points. Unlike the sun, which shifts its rising and setting points daily, a specific star always rises and sets at the same spot on the horizon if your latitude doesn't change much. For journeys largely along a single latitude, this was a perfect guide. Even with changes in latitude, experienced navigators understood how the star paths would shift. It was a system that demanded total immersion in the night sky, not just knowing constellations, but knowing the precise geography of the heavens as they intersected the horizon. And it shows an astonishing level of astronomical knowledge passed down orally and through practice. But how did they cope with cloudy nights, sometimes for days on end? Did they ever get lost when the stars were hidden? And how did they account for the subtle shifts in star positions over centuries due to precession, the slow wobble of the Earth's axis? Number 16. Did they use a magical stone to find the sun? The sunstone is one of the more mysterious and debated tools of ancient navigation, specifically associated with the Vikings. Legend and some historical texts suggest the Norse sailors might have used a crystal to find the sun's position even on cloudy days. This sounds like something out of a fantasy novel, right? But there's growing scientific evidence it might be true. The Icelandic sagas, particularly the Rodulfsthættir, mention a solarstein or sunstone used by King Olaf II of Norway. This story describes the king using it to find the sun's position on a snowy, overcast day. For a long time, historians thought this was just a myth. But then, in the 1960s, a Danish archaeologist named Thorkild Ramsku suggested that these sunstones might have been polarizing crystals. Crystals like cordierite or Iceland spar, calcite, have a special property: they can polarize light. Even when the sun is hidden behind thick clouds, the light from the sky still has a faint polarization pattern that radiates from the sun's position. By looking through one of these crystals and rotating it, a navigator could find the point where the crystal looks darkest or brightest. This point would indicate the sun's direction. Research by scientists like Gabor Horváth from Eötvös Loránd University in Hungary, published in the Proceedings of the Royal Society A in 2011, has shown that this method is indeed scientifically plausible. They conducted experiments using Iceland spar in various weather conditions and found that it was remarkably accurate, even under heavy cloud cover, to within a few degrees. Imagine being able to tell which way is west, even when you can't see the sun. This would have been a game changer for navigating the North Atlantic's often murky skies. This wasn't just a party trick, it allowed Vikings to maintain a course, especially in high latitudes where the sun's arc is low and days can be short in winter. They navigated across vast stretches of the North Atlantic to Greenland and North America, and accurate direction finding was essential. Without it, they'd be entirely reliant on dead reckoning and a good bit of luck. The discovery of a possible sunstone crystal, a piece of Iceland spar, in a 16th century shipwreck off Alderney in 2013 added more weight to the theory. While this specific crystal is much later than the Viking Age, it suggests the knowledge of such navigational aids persisted. It shows that people continued to understand the properties of these crystals and their potential uses. It's a testament to ancient ingenuity. They weren't just using brute force or simple observation. They were employing advanced physics, even if they didn't have the scientific language for it. They found practical applications for natural phenomena that we are only now fully appreciating. But what did these sunstones look like? Were they polished or just naturally occurring crystals? How common were they? And how did a Viking navigator sailing a small open boat in rough seas manage to precisely rotate and observe through a small crystal? Number 15, how did carved rocks guide ancient sailors? When we think of navigation, we often picture open oceans. But for many ancient cultures, sailing was about hugging the coast. And along those coasts, they left clues. Rune stones and other coastal markers weren't just for showing off, they were often practical navigation aids, especially for the Vikings and other maritime peoples. Imagine sailing a long coastline you know well. You'd recognize a distinctive mountain peak or a unique rock formation. But what if those natural landmarks weren't quite enough? Or what if you needed more specific guidance, say, into a tricky fjord or a hidden harbor? That's where carved stones came in. The Vikings, famous for their longships and far-ranging voyages, left thousands of runestones across Scandinavia and beyond. While most runestones commemorate individuals or events, some scholars, like Sven E. A. Nielsen, in his work on Viking Age navigation, suggest that certain stones with specific orientations or carvings might have served as navigational pointers. For instance, a stone might be placed at a crucial turning point, indicating a safe passage or a hidden inlet. It's not GPS coordinates, but a visual cue in a familiar landscape. Think about the sheer practicalities. A navigator might know that when the big rock with the serpent carving aligns with the Twin Peaks, then turn hard to port to enter the shallow bay. This kind of local knowledge passed down through generations would have been invaluable. These markers would be like ancient street signs, but for the sea, and it wasn't just runestones. Other cultures used similar methods. The ancient Egyptians, for example, had harbors that were carefully marked with large statues or specific architectural features. The famous Pharos of Alexandria lighthouse, built by the Ptolemies around 280 BC, was the tallest man-made structure of its time. It was a beacon, but also an unmistakable landmark, guiding ships from miles away into one of the busiest ports of the ancient world. Even simpler markers, like cairns piles of stones, could serve the same purpose on less developed coastlines. The accuracy here comes from local knowledge and repetition. A local fisherman or trading vessel captain would sail the same routes repeatedly. They'd memorize every distinctive rock, every specific tree, every subtle change in the coastline. And when they added their own markers, they were creating a reliable system. It was a way of standardizing navigation in an age without maps as we know them. Professor Niels Peterson, in his studies on Viking Age geography, has explored how Norse sagas often refer to specific landmarks, indicating that these features were well known and used for guidance. They were not just descriptive elements in a story, but navigational instructions. The sagas implicitly assume the listener or reader knows these places and how to use them. What we don't know how many of these runestones or other markers were primarily navigational and how many were just incidentally useful. Like, did a standardized system of coastal markers exist across a region, or were they more ad hoc and localized? And how did they deal with changes in the landscape over, centuries, erosion, tree growth, or even human alterations to the shore? Number 14, how did early sailors measure the sky with a disc? The astrolabe, specifically the planispheric astrolabe, is one of those instruments that screams ancient science. While often associated with astronomers and astrologers, early versions of the astrolabe were adapted for nautical use, especially by Arab and later European navigators. It was a sophisticated tool for its time, allowing sailors to measure the altitude of celestial bodies. An astrolabe is basically a two-dimensional model of the celestial sphere. It's a heavy disc, often made of brass, with various markings and moving parts. The key part for navigation was the alidade, a rotating rule with sights. A navigator would hold the astrolabe by a ring at the top, allowing it to hang freely and vertically. Then, they'd sight a star or the sun through the alidade's pinholes, and read the altitude wide, the angle above the horizon, from the engraved scale on the astrolabe's limb. Why was this accurate? Because the altitude of the North Star Polaris directly corresponds to your latitude in the northern hemisphere. If Polaris is 30 degrees above the horizon, you're at 30 degrees north latitude. For the sun, it's more complex, requiring calculations involving the date and time of year solar declination, but the principle is the same. By measuring the sun's altitude at noon, a sailor could determine their latitude. The earliest surviving nautical astrolabe dates from 1555, found in a shipwreck. However, earlier forms, known as mariners' astrolabes, are believed to have been in use since at least the late 15th century by Portuguese and Spanish explorers. And the astronomical astrolabe itself has a much older lineage, with origins in ancient Greece refined by Islamic scholars from the 8th century onward. But people like Muhammad al-Fazari, late 8th century, are credited with early versions. The work of navigation historians like Dr. Dava Sobel in Longitude highlights the critical need for latitude determination. While her book focuses on longitude, it underscores that latitude could be found relatively accurately with tools like the astrolabe centuries earlier. Christopher Columbus, for example, is known to have used an astrolabe and a quadrant, a simpler angle measuring device, on his transatlantic voyages in the late 15th century. He was often off by a few degrees, but his ability to return to specific latitudes was crucial. An astrolabe offered a quantitative, repeatable measurement. It moved navigation beyond pure observation and into the realm of applied mathematics. This wasn't guesswork, it was measurement. For example, if you wanted to sail to a specific port you knew was at 34 deg N, you would simply sail until your astrolabe showed Polaris at 34 deg altitude, or the sun at the calculated noon altitude for that latitude and day. But the astrolabe wasn't perfect. In a pitching and rolling ship, getting an accurate reading was incredibly difficult. The instrument had to hang perfectly still. So, how much did the swaying of a ship affect accuracy? Was it mostly used for approximate checks, or did truly skilled navigators manage high precision? And how did they keep them safe and dry on long voyages? Number 13, how did sailors use a small piece of wood to find their latitude? The Kamal is one of the simplest yet most ingenious tools for navigation from the Arab and Indian Ocean world. It's a small rectangular piece of wood, often with a string attached, and it allowed sailors to accurately measure the altitude of the North Star, Polaris, or the sun, thus determining their latitude. The basic idea is this: you hold the Kamal against your cheek, with the string held in your teeth. You slide the wooden rectangle up or down the string until its lower edge aligns with the horizon and its upper edge aligns with Polaris or the sun. The string is knotted at intervals, each knot representing a specific altitude or finger measurement, a unit called an isba, about 1.5 to 2 degrees. This method relied on the principle that if you know the angle of the North Star above the horizon, you know your latitude. If Polaris is 20 degrees above the horizon, you are at 20 degrees north. It's a direct measurement. The beauty of the Kamal was its simplicity and portability. No complex moving parts, just a string and a piece of wood. Historians like G.R. Tibbets, in his work Arab Navigation in the Indian Ocean before the coming of the Portuguese, extensively documented the use of the Kamal. He explains how Arab and Indian navigators used it to master the complex trade routes of the Indian Ocean, sailing from the coasts of East Africa to India and Southeast Asia. These voyages, dating back many centuries before European explorers, were regular and highly efficient. The Kamal made them possible. Portuguese explorer Vasco da Gama encountered the Kamal in the late 15th century when he rounded the Cape of Good Hope and entered the Indian Ocean. He was amazed by the precision of the Arab navigators. His own astrolabes were cumbersome and difficult to use on a moving ship, but the Kamal provided a quick, practical solution. A story says that Da Gama was shown how to use it by an Arab pilot, illustrating the advanced knowledge already present in the Indian Ocean. The Kamal's accuracy came from its direct measurement. Each knot represented a known angle. By noting which knot was against their teeth, or by using a Kamal with a movable piece, they could measure very precisely. It was particularly good for keeping a constant latitude. For example, if you wanted to follow a specific latitude, you'd just keep the star at the same knot position. This was vital for crossing wide stretches of ocean to find specific ports. It wasn't just a basic tool. Some Kamals had multiple pieces of wood or scales on the string, allowing for even finer adjustments. This simple tool was a cornerstone of ancient and medieval navigation across a massive and crucial trading region. But how did they get the initial knot measurements so accurate? Did each navigator make their own Kamal, or were they mass-produced? And how did they deal with the natural variations in a person's arm length, or how they held the string, which could subtly affect the measurement? Number 12. How did a magnetic rock first guide sailors? The magnetic compass changed everything. It was a revolutionary tool, but its origins are much older and more debated than most people realize. The earliest form of a magnetic compass was not the ship's compass we recognize today, but a simple piece of magnetized iron, or lodestone, floating in water. The first reliable accounts of a magnetic compass come from China, dating back to the Han Dynasty 206 BC8, 220 AD. These early compasses were used for geomancy for aligning buildings auspiciously. They were called south-pointing fish or south-pointing spoon for a lodestone spoon on a bronze plate. The idea was simple. A magnetized needle, when allowed to pivot freely, naturally aligns itself with the Earth's magnetic field pointing roughly north-south. By the Song Dynasty 960 to 1279 AD, the magnetic compass was definitely being used for navigation at sea. The scientist Shen Kuo described in his Dream Pool Essays 1088 AD a magnetic needle that could point south, mentioning its use by navigators. And in 1119 AD, Zhu Yu's book Pingzhou Catan explicitly states, the pilots steer by observing the sun in the day, the stars at night when the sky is dark and obscure, they look at the south-pointing needle. This is definitive evidence of maritime use. The compass provided a constant direction reference, regardless of weather. Before the compass, if the sun or stars were hidden, sailors relied on dead reckoning, current knowledge, and prayers. The compass offered an objective, always-present guide to direction. This dramatically reduced risk and increased the feasibility of open ocean voyages. It allowed Chinese navigators to sail further and with more confidence into the Indian Ocean, reaching Africa and the Middle East, as famously documented by Zheng He's treasure fleet voyages in the early 15th century, though compasses were used long before then. It arrived in Europe much later, around the late 12th century, likely transmitted through Arab traders. Alexander Neckham, an English monk, described a magnetic compass for navigation in his work, De Naturis Rerum, in 1190 AD. The accuracy came from the Earth's consistent magnetic field. While magnetic north is not exactly true north and shifts over time magnetic declination, for practical purposes over short to medium distances and within a navigator's known routes, it was incredibly reliable. Mariners learned to account for local variations. It meant you could steer a consistent course even if you couldn't see anything around you. The compass essentially freed navigators from total dependence on celestial bodies. It allowed for true all-weather 24-hour direction finding. It was a foundational technology that enabled the age of exploration. But how did ancient sailors understand why the needle pointed north? Did they attribute it to magic or unseen forces? How did they keep their early crude compasses from being affected by iron tools or weapons on board their wooden ships? And how did the Chinese secret of the compass make its way to Europe, a journey of many centuries? Number 11. How did the ocean's colors and temperatures tell a story? The ocean isn't just a uniform blue, its color changes, its temperature shifts. For ancient navigators, these subtle variations were critical clues, telling them about depth, currents, proximity to land, or even what kind of land was nearby. It was like reading a detailed map without any paper. Consider watercolor. If you're in the deep ocean, the water is usually a dark, clear, deep blue. But as you approach land, especially coasts with rivers, the water can become greener, murkier, or even brown from sediment. All rivers bring runoff full of nutrients and particles, which change the water's optical properties. The discharge of the Amazon River, for example, can be seen far out at sea, a distinct plume of lighter, murkier water. Ancient sailors would recognize this. Dr. Genevieve J. Long, in her studies of oceanography and navigation, often highlights how these changes in water properties were fundamental to pre-instrument navigation. She points out that the shift from deep blue to turquoise could signal a coral reef or shallow bank, meaning a change in depth. This was vital to avoid running aground. Water temperature was another key indicator. Ocean currents have different temperatures. The Gulf Stream, for instance, carries warm water far north into the Atlantic. Ancient Norse sailors, venturing into the North Atlantic, might have noticed warmer currents, signaling that they were still within the influence of these warmer waters, possibly indicating a path towards Europe or even a specific fishing ground. Conversely, a drop in temperature could mean entering colder, polar waters or a different current system. The Polynesians were also masters of this. They would often put their hand in the water to feel temperature changes. A slight warming might indicate proximity to a large island, which can affect local water temperatures. A change in salinity, which can correlate with temperature and color, might also be detectable by taste, indicating freshwater sources or specific current patterns. This method was based on direct sensory input. It wasn't about calculations or instruments, but about acute observation and experience. A navigator who had sailed a route many times would learn the specific look and feel of the water at different points along that journey. They knew what a certain shade of green meant or what a sudden chill implied. For example, when sailing towards the Cape Verde Islands off West Africa, Portuguese navigators in the 15th century learned to look for changes in water color and signs of marine life as they left the clearer Atlantic waters and approached the greener, more productive waters closer to land. It was a confirmation of their course and an early warning of an approaching coast. But how precise could these observations be? Did a shift in color always mean land, or could it be a deep ocean upwelling? And how did they share and pass on such subjective sensory knowledge across generations without a common scientific language? Could a change in water taste reliably distinguish between different rivers or freshwater sources? Number 10, could they smell land before they saw it? This sounds almost unbelievable, like something out of a myth, but ancient navigators truly could, and did, use their sense of smell to detect land long before it was visible. The ocean carries scents, and specific landmasses have unique olfactory signatures that can travel surprising distances on the wind. Imagine being at sea for weeks. Your senses become incredibly heightened. A subtle shift in the air, a faint aroma that is not the salt of the sea, would be a strong signal. What kind of smells are we talking about? One common scent is that of vegetation. Lush tropical islands, with their dense rainforests and flowering plants, release distinctive odors. The scent of damp earth, decaying leaves, or specific flowers could be carried by prevailing winds for tens, even hundreds of miles. Researchers like Dr. Wayne S.C. Gutzlaff, who studied traditional navigation, have often pointed to the importance of land smell in the Pacific. Polynesians, for instance, speak of the sweet smell of flowering plants, or the earthy smell of volcanic soil. Another smell could be smoke. If there were active volcanoes on an island, or if people were burning fires for cooking or clearing land, that smoke could drift far. Even the smell of decaying organic matter from lagoons or mangrove swamps could indicate a specific type of coastal environment. The Viking sagas sometimes mention land smell. While not scientific texts, they reflect the observational knowledge of the time. When Norse explorers approached North America, they would have likely experienced the strong smell of pine forests carried by westerly winds. This would be a stark contrast to the open ocean and a clear sign of a large landmass. Studies on scent perception, though not directly on ancient navigation, confirm that humans can detect incredibly faint traces of volatile organic compounds. The key is concentration and familiarity. An experienced navigator, intimately familiar with the smells of various islands and coasts, would be tuned to these subtle changes. They wouldn't just smell something, they might smell that specific island. This method wasn't about pinpointing an exact location. It was about confirmation. If your dead reckoning or star observations suggested you were nearing land, and then a distinct land smell reached you, it would boost confidence immensely. It would tell you, yes, you are on the right track, keep going. It was an additional layer of verification in a complex system of cues. It shows an incredible reliance on all human senses, not just sight. In a world without instruments, every sensory input was a potential piece of data for navigation. The human body was the most sophisticated sensor array available, but how far could these smells truly travel? Would strong winds or rain dissipate them quickly? And how did navigators distinguish between the smell of a known island and a completely new, uncharted landmass they were hoping to discover? How much of this smell was real chemical detection, and how much was psychological, heightened awareness based on expectation? Number 9, how did ancient sailors read the sky for storms? Well, weather forecasting without satellites or computer models seems impossible. But ancient navigators were incredibly adept at reading the sky and the sea to predict weather, often with surprising accuracy. This wasn't just about avoiding a little rain, it was about survival. Knowing a storm was coming could mean the difference between life and death at sea. Their methods relied on deep observation of cloud formations, wind shifts, and changes in the ocean's surface. A critical part of this was understanding patterns. Different cloud types signal different weather conditions. Cumulus clouds might mean fair weather, but towering cumulonimbus clouds, especially with anvil-shaped tops, scream thunderstorm ahead. Ancient mariners knew this. They recognized the dark, brooding look of a squall line approaching. The Polynesians, for example, were masters of this. They studied how clouds formed over land, even over islands far below the horizon. The moisture rising from a tall island could create a specific cloud cap or cloud line that could be seen from many miles away. David Lewis, in his work on traditional navigation, describes how Mao Piailug could spot these land clouds and use them to guide his course. This wasn't just predicting weather, it was using weather to find land. Wind shifts were also vital. Sailors felt the wind on their skin, saw its effect on the sails, and heard it in the rigging. A sudden drop in wind speed, followed by an unusual lull and a shift in direction, often indicates an approaching frontal system or storm. A rising barometer today tells us this ancient sailors used their senses. The Roman author Virgil, in his epic Aeneid, mentions sailors observing cloud signs, like the shining stars hidden by darkening clouds as a storm approaches. This reflects a common practical knowledge of the time. Pliny the Elder, in Natural History, also offers extensive advice on weather signs, from cloud formations to the behavior of birds and even the color of the sea. The accuracy of this method came from constant, lifelong observation. These navigators weren't just looking at the sky once in a while. They lived under it, they developed an intimate understanding of local weather patterns, seasonal shifts, and the subtle precursors to severe weather. They knew that a certain type of halo around the sun or moon could signal rain. They knew that a specific color in the dawn sky meant trouble. This detailed weather knowledge allowed them to choose optimal sailing times, avoid dangerous routes, or seek shelter when necessary. It wasn't about being perfectly right every time, but about significantly reducing risk. But how much of this weather forecasting was genuinely predictive versus simply reacting to immediate changes? Did they have ways to communicate complex weather predictions to other ships in a fleet, or was it mostly individual intuition? And how did they deal with truly unexpected sudden storms that showed few warning signs? Number 8. What did fish and whales tell ancient explorers? The sea is full of life, and for ancient navigators, marine animals were not just food, they were living navigation buoys. Observing specific fish, birds, whales, seals, or even plankton could provide critical information about currents, water depth, proximity to land, or even the direction of a known fishing ground. This was a form of biomarker navigation. Take birds, for example. We'll talk about bird migration more broadly later, but specific seabirds have distinct foraging ranges. If you're deep in the open ocean and you start seeing terns, noddies, or frigate birds that are known to roost on land every night, it's a strong signal that land is relatively close, perhaps within 50 to 100 miles. And if those birds are flying consistently in one direction at dawn and returning at dusk, they're showing you the way to their roosting island. This was a primary method for Polynesians finding new islands. Archaeological studies, like those by Patrick Vinton Kirch on Pacific Voyaging, have highlighted the role of ecological cues. He discusses how navigators learn the habits of certain fish schools or the presence of specific marine mammals as indicators of particular ocean features or landmasses. Whales and seals also provided clues. Some species, like humpback whales, follow seasonal migration routes. If you knew these routes, spotting whales could confirm your position along a predictable path. Live seals often haul out on land or ice floes, so seeing them would indicate proximity to land, especially in colder regions like those navigated by the Norse. And fish schools were also important. Different types of fish inhabit different parts of the ocean. The presence of specific schooling fish might indicate areas of upwelling, which often occur near landmasses or seamounts. A sudden abundance of bait fish could mean you're in a productive area, often linked to coastal environments. And even plankton could be a clue. Some bioluminescent plankton glows in the dark, and its presence or absence could indicate different water masses or currents. While this is a subtle cue, highly experienced navigators attuned to every detail might have picked up on it. David Lewis describes how Pacific Islanders learned to identify fish, highways, predictable paths that fish schools would take between islands. Navigators used these invisible highways, knowing that following them would lead to another island. This was less about random sightings and more about understanding predictable ecological patterns. This method was astonishingly accurate because the behavior of animals is often tied to predictable environmental factors like food sources, breeding grounds, and migration routes. If a navigator understood these ecological relationships, the animals effectively became living guides. But how did they distinguish between a temporary random bird passing by and a bird reliably indicating land? Did they ever mistakenly follow animals that were simply lost or foraging unusually far from their usual habitats? And how did they transmit this complex, nuanced ecological knowledge across generations without written records? Number 7, how did a weighted rope prevent shipwrecks? One of the most practical and crucial methods for ancient coastal navigation was depth sounding. It sounds simple, just measure how deep the water is. But this was incredibly important for avoiding hidden shoals, reefs, and finding safe anchorages, especially when approaching unfamiliar coasts or sailing in foggy weather. The tool was a lead line. This was a rope, often marked at specific intervals, with a lead weight attached to one end. A sailor would cast the lead line overboard and let it sink to the bottom. They would then pull it back up, counting the marks on the rope to determine the depth. The marks were often made with different colored cloths or pieces of leather, representing specific fathoms. A fathom is about 6 feet, or the length of a man's outstretched arms. The lead line wasn't just about depth. The bottom of the lead weight was often hollowed out and filled with tallow or grease. And when the lead hit the seabed, a sample of the bottom material, sand, mud, shells, pebbles, would stick to the tallow. This sample was incredibly valuable. A navigator could analyze it. Different types of seabed meant different locations. For example, a sandy bottom might indicate a beach, while a muddy bottom might suggest a river mouth or sheltered bay. A rocky bottom could mean a reef or a dangerous area. This method was in use for thousands of years. The ancient Egyptians, Phoenicians, Greeks, and Romans all used lead lines. The Greek historian Herodotus, 5th century BC, describes how Egyptian sailors used lead lines in their trade. The Bible in Acts 27 recounts how Paul's ship, caught in a storm, sounded the depth, finding it first 20 fathoms, then 15 fathoms, indicating they were nearing land. This was a matter of life and death for ancient mariners. Captain Matthew Flinders, the British explorer who mapped Australia in the early 19th century, was a big proponent of lead line navigation. His charts always included depth soundings and descriptions of the seabed, showing its continued importance even as other instruments developed. The accuracy came from its directness. You were getting real-time, concrete data about the immediate environment. And it wasn't just a single reading. By taking repeated soundings, sailors could determine if the water was getting shallower or deeper, and how quickly. This allowed them to feel their way into harbors or around dangers, even when visibility was poor. It was a slow method, especially in deep water, but it was reliable, and the information about the seabed material was a crucial additional layer of data that modern depth sounders don't provide in the same way. It confirmed what the navigator might suspect from other signs like watercolor or the scent of land. But how did they get accurate readings in rough seas when the lead line would swing? How many different types of seabed material could an ancient navigator reliably identify? And did they have standardized charts of seabed types for different coastal areas, or was it purely local experiential knowledge? Number 6, how did they guess their way across oceans? Dead reckoning sounds like a grim term, but it's one of the oldest and most fundamental navigation methods used by every mariner, ancient or modern. It's essentially the art of estimating your current position based on your last known position, then factoring in your speed, direction course, and how long you've been traveling. Imagine, you started at point A, you sailed east at 5 knots for 10 hours. Simple math tells you you're now 50 nautical miles east of point A. That's dead reckoning in its purest form. It doesn't rely on outside observations like stars or land. It relies on internal measurements and estimates. Ancient navigators used various methods to estimate speed. They might throw a piece of wood off the bow and time how long it took to pass a certain point on the stern. Or they simply learned to feel the speed of the ship through the water. Direction was maintained using celestial bodies, wind direction, or later, a compass. Time was estimated by hourglasses, sandglasses, or simply by the sun's position. Historians of navigation, such as Peter C. Spears, often highlight dead reckoning as the backbone of all ancient voyaging. Without it, celestial observations would just give you a latitude or a general direction, but not a precise plot of your journey. All explorers, from the Phoenicians in the Mediterranean to the Vikings in the North Atlantic, used dead reckoning. But Christopher Columbus kept meticulous records of his courses and speeds, constantly calculating his estimated position, even if his figures were sometimes inflated for political reasons. The accuracy of dead reckoning depended heavily on the skill of the navigator. A good navigator had an intuitive feel for speed, could keep a consistent course, and was good at mental math. They would also try to account for currents and wind drift, which could significantly alter their actual path. If they knew the prevailing current was pushing them south at 1 knot, they would factor that into their calculation. This required vast experience. It was a continuous process. Every hour, every watch, the navigator would update the ship's estimated position. This cumulative effect meant small errors could compound over long voyages. This is why other methods like celestial navigation were crucial for fixing the position, getting a fresh, accurate starting point from which to continue dead reckoning. This method provided a continuous plot of the journey, a mental or physical map of where the ship had been and where it was likely headed. It was the constant thread that tied all other more intermittent navigational observations together. But how accurate could their speed estimates truly be without mechanical logs? How did they account for complex shifting ocean currents that weren't obvious? And what happens when a storm pushes a ship violently off course, making all previous dead reckoning calculations obsolete? Number 5, how did the moon's cycles help them cross oceans? The moon is more than just a pretty light in the night sky. For ancient navigators, it was a precise timekeeper and a valuable navigational aid. Its phases, its position, and its influence on tides offered crucial cues for finding direction, timing coastal movements, and even estimating longitude. Lunar cycles are incredibly regular. The moon goes through its full cycle of phases: new moon, quarter, full moon approximately every 29.5 days. This predictability made it an excellent calendar and a way to track time at sea. Knowing the date was important for celestial navigation, especially when using the sun to determine latitude, as the sun's declination, its angular distance from the celestial equator, changes daily. The moon helped them keep track of the days, but the moon itself was also a direct navigational aid. Like stars, the moon rises and sets at specific points on the horizon. A navigator could use its rising or setting position as a directional guide, similar to how they use stars. However, the moon's position shifts significantly throughout its cycle, so a deeper understanding of its movement was needed. Perhaps even more important was the moon's influence on tides. For coastal navigation and entering harbors, understanding tides was critical. The moon's gravity is the primary driver of tides. High and low tides occur at predictable intervals, roughly twice a day, shifting by about 50 minutes each day. And ancient mariners, especially in regions with strong tides like the North Sea or the Bay of Fundy, developed intricate knowledge of these patterns. They knew when to enter a shallow harbor with the incoming tide or when to leave with the outgoing tide. This knowledge often meant the difference between smooth sailing and running aground. The Phoenicians and Romans, navigating the Mediterranean, where tides are less pronounced, still paid attention to any tidal currents in narrow straits. But the Vikings, operating in the Atlantic, would have needed extensive tidal knowledge for their coastal raids and exploration. The Professor Niels Peterson, in his work on Viking maritime culture, points out that tidal knowledge was passed down orally and was crucial for their mastery of northern waters. Later, in medieval Arabic and European navigation, the moon's position relative to specific stars could even be used to estimate longitude. This method, called lunar distance, involved complex calculations, but was known to be theoretically possible long before chronometers made longitude finding easy. People like the Arab astronomer Ibn Yunus, 10th century, developed tables for lunar distances. It wasn't simple, but it showed how deeply they understood the moon's motions. The moon offered predictability in the ever-changing sea. It was a constant, dependable celestial clock and a powerful force influencing their immediate environment. But how accurately could they predict tides without written tide tables, especially in new, uncharted areas? How did they visually measure the moon's position with enough precision for navigation given its rapid movement? And did ancient sailors understand the gravitational forces causing tides, or was it simply observed as a natural, rhythmic phenomenon? Number 4, how did the sun's path guide them across the world? The sun is the most obvious celestial body, and ancient navigators used it relentlessly. It wasn't just about telling day from night. They extracted incredibly precise information from its daily and seasonal movements, its height in the sky altitude, its direction azimuth, and its position at noon. This allowed them to determine both direction and latitude. The simplest use was direction. The sun rises generally in the east and sets generally in the west. If you watch where it rises and sets, you get a good sense of cardinal directions. But more accurately, at noon, the sun is at its highest point in the sky and lies directly to the north or south, depending on your hemisphere and the time of year. Knowing this true noon direction was a constant reference for keeping a course. For determining latitude, the sun's noon altitude was key. Navigators would measure the sun's height above the horizon at local apparent noon using a simple quadrant, a comal, or later an astrolabe. By comparing this altitude to known tables of the sun's declination, its position relative to the celestial equator, for that specific date, they could calculate their latitude. For example, if you measure the sun at 90 degrees directly overhead, you are on the subsolar point, which is the latitude equal to the sun's declination for that day. This method was particularly accurate for mariners in the tropics. Near the equator, the sun passes directly overhead twice a year. The Polynesian navigators, often sailing close to the equator, would learn that certain islands corresponded to times of the year when the sun was directly overhead. This meant if the sun was at your zenith, straight up, you were at the specific latitude of the subsolar point for that day. This precise observation was an anchor point in their navigation system. Dr. David Lewis, in his seminal book We, the Navigators, details how Pacific Islanders used these zenith passages. They knew which stars or constellations passed directly overhead for each island. Similarly, they tracked the sun. It was a natural, built-in GPS for tropical navigators. The Greeks and Romans also used the sun extensively. The gnomon, a simple stick stuck in the ground, could cast a shadow that changed length and direction throughout the day, providing time and direction. By measuring the shortest shadow at noon, they could determine the sun's zenith distance and thus their latitude. And Eratosthenes of Cyrene, around 240 BC, famously used sun angles in Alexandria and Syene to calculate the Earth's circumference with surprising accuracy. His method was fundamentally a form of solar navigation. The accuracy came from the sun's predictable movements. With a clear day and practice, a navigator could get a latitude reading accurate to within a degree or two, sometimes even less. This was crucial for hitting a desired parallel of latitude and then running down the easting or westing until land was sighted. But how did they get precise noon readings on a moving ship, especially without accurate clocks to know the exact moment of local apparent noon? How did they account for atmospheric refraction, which can make the sun appear higher than it actually is? And how did navigators, without written tables of solar declination, memorize or deduce these changing values throughout the year? Number 3, how did birds show them hidden lands? Bird migration is one of the most remarkable phenomena in nature, and ancient navigators, with their keen observational skills, used it as a powerful living navigation system. Birds, especially seabirds, are not random. Their presence, type, and flight direction could tell a sailor a huge amount about proximity to land, the direction of that land, and even its specific nature. For thousands of years, Pacific Islanders, Arabs, and even early European sailors observed birds. When you're out on the open ocean and you start seeing land-based birds or seabirds that are known to roost on islands, it's a huge sign. Many seabirds, like terns, frigate birds, and boobies, forage far out at sea during the day but return to land every night to rest. And Polynesian navigators, for example, would watch these birds at dawn and dusk. If a flock of birds flew consistently in one direction at sunrise, they were likely heading towards their home island. At sunset, they would fly back. A skilled navigator would simply follow them. This was not a guess, it was following an instinctual, reliable guide. Dr. David Lewis, in his many field studies with Pacific navigators, documented this extensively, showing how bird paths were integral to their wayfinding. Mau Pialug, the Micronesian master navigator, relied heavily on bird behavior during the Hokulea voyages. The ancient Arabs also used birds. Sailors in the Indian Ocean would sometimes release birds like crows or pigeons that they brought on board. If the bird circled and then flew off purposefully in one direction, it was assumed to be heading towards land, and the ship would follow. If it circled and came back to the ship, it meant no land was in sight. This practice is mentioned in ancient texts and was observed by European explorers like Vasco da Gama when he met Arab pilots. Viking sailors also likely relied on bird sightings in the North Atlantic. Seeing specific land birds or even certain types of sea ducks could indicate proximity to different landmasses like Iceland, Greenland, or the coast of North America. The Norse sagas contain hints of using birds for guidance. The accuracy of this method came from the predictability of bird behavior. Birds need land to breed, nest, and often to rest. Their foraging ranges are generally known to experienced observers. It wasn't about a single bird, but observing patterns and understanding species' specific habits. If you knew a certain type of shearwater nested on a particular island, its presence was a direct pointer. This method was particularly useful when land was just over the horizon, maybe 50 to 100 miles away, or even further if the birds were large and flew high. It turned an empty seascape into one full of potential direction cues. But how did ancient navigators distinguish between birds that were truly indicative of land and those that were simply lost or offshore for other reasons? Did they ever mistakenly follow birds that led them astray? And how did they adapt this knowledge when they were exploring completely new regions with unfamiliar bird species? Number two, how did they ride the ocean's invisible roads? Imagine the ocean surface as a complex, ever-moving map, full of invisible roads. This is how Polynesian and Micronesian navigators viewed ocean swells. They didn't just see random waves, they saw distinct, predictable patterns of swells generated by distant storms and deflected by unseen islands. This was one of the most sophisticated and shocking accurate navigation methods. Ocean swells are long, low waves that can travel thousands of miles across the open ocean. They originate from storm systems far away and continue even after the storm has passed. These swells have a direction, a period time between crests and a height. But critically, when swells encounter an island or an island chain, they are refracted, they bend around the obstacle, and they also reflect off it. And this creates complex interference patterns. A master navigator, like the Micronesian navigators of the Marshall Islands, could read these patterns. They would lie down in the canoe or sit with their back to the mast to feel the subtle differences in the canoe's motion caused by intersecting swell patterns. They could distinguish between direct swells from a distant storm, refracted swells bent around an island, and reflected swells bounced off an island. The interaction of these swells created a unique signature around each island. The most famous example of this knowledge is the Micronesian stick chart. These were not maps in our sense, they were mnemonic devices made of sticks representing swells and shells representing islands. They weren't geographically accurate in scale, but they accurately depicted the relationship between islands and the complex swell patterns they generated. Dr. David Lewis in We, the Navigators, dedicates significant portions to explaining how these charts represented a profound understanding of ocean physics. This method allowed navigators to detect the presence of islands that were still far below the horizon. They could determine the direction of an island not by seeing it, but by feeling its influence on the waves. This was especially crucial for finding low-lying coral atolls, which are almost impossible to spot visually until very close. Modern oceanographers confirm the physics behind this. Swell patterns do indeed behave this way. What is shocking is that ancient navigators understood and utilized these complex wave mechanics purely through observation and embodied knowledge, without mathematical models or instruments. Their bodies were the sensors and their minds were the processors. For a navigator like Mau Pialug, who navigated the Hokulea, the feel of the swells was constant confirmation or correction of his course. When clouds obscured the stars or when the sun was hidden, the swells became the primary guide. He could tell if the canoe was holding its course or if a current was pushing it off by the way the waves felt against the hull. But how did they maintain such sensitivity over days and weeks of constant motion? Did different navigators feel the swells in slightly different ways, leading to potential discrepancies? And how much of this knowledge was truly universal across the Pacific versus highly localized to specific island groups and their unique swell environments? Number one, how did a mental map of the stars guide Pacific voyagers? This is perhaps the most famous and astonishing of all ancient navigation methods, the Polynesian star compass, or sidereal compass. It wasn't a physical object you held in your hand, it was a complex, sophisticated mental map of the stars and their fixed rising and setting points on the horizon, allowing navigators to hold a precise course across thousands of miles of open ocean. Imagine a full circle around your canoe representing the horizon. Polynesian navigators divided this circle into 32 or more houses or directions, each corresponding to the precise point where a specific star or constellation would rise or set. They memorized hundreds of these star paths. So the star compass wasn't just Polaris for north. It was House of Sirius, House of Pleiades, House of Southern Cross, each indicating a distinct direction. When a navigator set a course, they would pick a guide star from their mental compass that rose or set in the desired direction of their destination island. They would steer the canoe towards that star, As the Earth rotated and the first guide star moved across the sky, another star would rise or set in the same house or direction. The navigator would then switch their focus to the new star, maintaining the course. This constant shift from one guide star to the next, often without ever taking their eyes off the horizon, allowed them to maintain a remarkably straight path. This system was documented and taught by master navigators like Mau Pia Lug from Sarawal, Micronesia, who famously navigated the Hokulea from Hawaii to Tahiti in 1976 using only traditional methods. His knowledge and the successful journey of Hokulea proved that this ancient art was not only possible but incredibly accurate. The Polynesian Voyaging Society has since sailed Hokulea around the world using these methods. The accuracy came from the fixed nature of star positions relative to the horizon at a given latitude. While the sun's rising and setting points shift daily, a star's rising and setting points are essentially constant. This provided unshakable bearings. Even if a navigator knew their latitude was changing, they understood how the star paths would appear to shift and could compensate. But the star compass was more than just direction. It was integrated with other methods. Navigators used it alongside their understanding of ocean swells, bird migrations, and cloud formations. If the stars were obscured by clouds, they would rely on the feel of the swells, always holding the mental star compass in their mind's eye to verify their heading. This system represents an unparalleled feat of human memory, observation, and astronomical understanding. It was passed down orally for generations, often in chants and stories, turning celestial mechanics into practical, embodied knowledge. These navigators were true scientists without laboratories, using the entire ocean and sky as their classroom. But how did they pass on such a complex mental map of hundreds of stars without writing? And did the star compass vary significantly between different island groups, or was there a common underlying structure? And what happens when a long storm obscured the stars for days or weeks, forcing complete reliance on less precise methods for extended periods? How did they regain their true course after such a blind period?